Hello, and this is the chapter 5. I have some good news for you. This is gonna be second to last chapter because we have 6 chapters, right? And this is the 5th chapter. So the chapter 5 and chapter 6 are gonna be very short compared to the first 4 chapters. The chapter 3 was the longest one, and chapter 4 was a little bit long, okay? But for chapter 5 and chapter 6, it is very short, okay? So with a blink of an eye, we can see that we're at the end, okay? And we have a little surprise at the end of the class 2. So please stay tuned, okay? So in chapter 5, because in the first 4 chapters, we talk much about the theory, about the expectation, conditional expectation, about the PDF and so on. So in chapter 5, I'm going to relax a bit and talk about the practical aspect. That is, we are going to discuss some frequently used distribution. For many distributions, we have talked a little bit about it in, let's say, chapter 3 and chapter 4, but we didn't have time to dig so much about it. This is the space for the chapter 5, okay? So for the chapter 5, you can expect that there will be no content, no new content, but it's going to be like a review and we talk about the practical aspects of distribution together. And in this lesson 36, we talk about the binary, binomial, and hypergeometric distribution. So let's begin. Binary, we have 2 possible outcomes, like 0 and 1. It's going to be like tossing a coin, right? For the binomial, it's tossing a coin for n times. Okay, we have success and failure. And with some of them, we can, let's say, from the n trials, how many coins we get hit. Okay. And for the hypergeometry, if we sample a fixed number of units from that population, what is the number of successes? So if we pick one member from the population, we will not pick them again. Okay. So the binary distribution is simple as this one. Okay. Probability that x equals 1 is p and x equals 0 is 1 minus p. So a little bit of notation. We can write it in this way. It is more convenient. Okay, it is more convenient. Because what? If x equal to 0, what does it mean? P0, 1 minus P1 is going to be 1 minus P. If x equal to 1, what's equal to? P1, 1 minus P0 is going to be P. Yes, let's a shorter way, the equivalent way to talk about this kind of distribution, okay? So EX is P, EX squared is P, rest of P times 1 minus P, and sine of X is E to the power ETH. It's going to be PET plus 1 minus P. So this one is easy. So we can get it's an easy homework, okay, to do it at home, and I'm going to show you here. So this chapter is a little bit of that's like the review, okay? So we will not talk about the heavy content here, okay? For the binomial distribution, this similar, you have seen this before, right? In, let's say, from chapter 1, I guess, okay? So if the random variable x1 to xn form n binary trials with parameter p, and if x equal to x1 up to xn, then x has the binary relation with parameter s and p. So this is obvious, but if you want to do the proof, okay, you can see the textbook on try as your homework, okay? So this one is intuitive. So the binomial distribution, we have EX because we can say that x equal to x1 plus up to xn. So we can say that E of x is what? N EX1. And EX1 is NP, right? And variance because similar thing. And for this one, because, okay, so you can write this one, right? T of what? X1 plus up to xn. because they are independent, x1 until xn are independent, that is, we can tx1 and we get what? PET plus 1 minus p to the power of n. Okay. Next up, hypergeometric distribution. We have x of fx of a, b, and n. Okay. This one, I think we have seen this from chapter 1. All right, from chapter 1 already. So e of x. Okay. So this similar manner, it is e of x1 up to xn. And for each one, it's going to be what? Nex1. And where is this one? N of a plus b. Okay. And for the variance of x, okay, for the variance of x, we can say that x1 up to xn, it is what? We can get this number, right? Because what? Because, so remember, we cannot write something like n times each terms of the variance, right? So the thing that we should do is that we sum off this and take the variance of this one together. We cannot separate the sum. If we want to separate the sum, we get the variance of xi plus let's say 2, right? Covariance. So the covariance is not equal to 0. Okay. That is what we are going to prove next. The covariance of x1 is equal to this one. So the key to prove, okay, is to set variance of x equal to 0 when n is equal to a plus b. So if we draw off them, surely we get a certain outcome. Okay, and we can plug into this one into the previous formula of the variance. Okay, and this suggests that the covariance is not equal to what? 0. And we can use it to derive the variance too. Okay, so you can leave this as homework. We are not going to go to this as detail because we have learned about it in, let's say, chapter 4 already. Okay, so I'm here to explain the practical aspect. So, and this one is the practical aspect. Okay, so there are relationship between the binomial and hypergeometric. I have said that binomial is just tossing the coin n times, and hypergeometric is that picking the population at each time. So if we, let's say, define the success of hypergeometric to be that, okay, we pick the right population that we select. So it's gonna be similar, but how do we quantify this as the mathematics? So mathematically it's true, but how do we quantify it? Okay, so let's go to this statement together. So let p between 0 and 1 and let n be a positive integer. Let y have the binomial distribution with parameters n and p. For each positive integer t, at and bt be integers such that limit of at is infinity, limit bt is infinity. That is, each population go to infinity, but the proportion is p. It's like tossing a coin. Okay, if let's say tossing a coin for finite time, if all come at infinity, so it is very similar to the binomial, right? And let xt be hypergeometric distribution with parameter a, t, b, t, and n. So if we take this ratio and we take t to the infinity, this is equal to 1. That is, these two are very close to each other when when the number of sample is large. Okay, and that's all for this lesson. And in the next lesson, we're going to talk about the Poisson distribution. So see you next time.